We will rocket across continents at the speed of a jet, float above tracks made from pure air, and journey through the center of the Earth. Technology is pushing from every direction, getting faster with each passing second. Prepare yourself. The future is closer than you think. Most people think of the train as a 19th century relic, the workhorse of an industrial age. But for visionaries around the world, the potential of trains is unlimited and may be the key to solving our most stubborn problems.
Because of the rising cost of fossil fuels, we're gradually going to have to make a transition away from the automobile to mass transit and to trains. Because trains are perhaps the most efficient and the most cost-effective way to move large amounts of people.
Could trains replace airplanes as our long-distance ride of choice? Maybe, if they were fast enough. When it comes to getting from point A to point B, the ultimate selling point is speed. So what's been keeping trains from meeting our need for speed? Friction. Friction is the force that slows down movement between any two surfaces, like wheel and rail, or tire and road.
It's friction that absorbs most of the energy of our energy-consuming society. Realize that when you get in a car and you put in gasoline, where does the energy go? It goes to overcoming friction, the friction of your tires on the road. If you were to ride on a frictionless road, it's like being an ice puck on an ice skating rink. How much energy does it take to send that ice puck across the skating rink? Almost zero, because it floats.
A hockey puck floats on a thin layer of melted ice. But how would it be possible to make a train float? By using super powerful magnets.
One of the most fantastic technologies that could revolutionize everything is supermagnets.
Magnetic levitation is a technology that's been experimented with for years. But new advances mean that the era of floating high-speed trains could be coming soon.
This is the system of the future. It's 300 miles per hour. It's emissions-free, no foreign oil. It's green, it's fast, it's comfortable, and it's kind of sexy.
Maglev can immediately get you a step beyond where the current state-of-the-art system is, and you've got a new starting point to evolve a new technology.
Most magnetically levitating, or maglev trains, use electromagnetic suspension. The bottom of the train wraps around the track, and magnets embedded in the train pull up toward the rail, lifting the train.
One of the exciting things about maglev is because it floats on a cushion of air, it's contact-free.
This means it can hit high speeds with extreme efficiency. Maglev uses about half the energy per passenger of a commercial plane. A few maglev trains are already in service, and they're breaking records. In Japan, the ML-X01 hit 361 miles per hour on a test track. In Shanghai, a 19-mile trip to Pudong Airport that takes 1 hour by car takes 7 minutes and 20 seconds on the Shanghai Maglev. That's because the Maglev reaches 220 miles per hour in 2 minutes.
People like speed, they like moving quickly, as long as it's safe. Maglev is proven safe. It's impossible for this train to derail.
It can't derail because the train actually wraps itself around the track. Because it's so safe and so fast, the American Magline Group has come up with an audacious plan to connect two of America's most popular destinations: Disney's home in Anaheim, California, and Las Vegas in Nevada. Today, these two hotspots are connected by a highway, but separated by lots and lots of traffic.
40 million people a year travel along I-15 between Southern California and Southern Nevada.
a heavily congested corridor which is experiencing a tremendous amount of growth.
In traffic, the 261-mile car trip takes over 5 hours and a lot of gas. But the AMG Maglev will take that same journey in 90 minutes, averaging 180 miles an hour and reaching a top speed of 310 miles per hour.
You know, the capacity of this system is equivalent to an 8-lane freeway. It can move a lot of people quickly. It's the equivalent of 50 747s landing every hour.
Moving that many people quickly and cheaply between cities would be a transportation breakthrough. But other Maglev pioneers think the technology also has amazing potential for moving us within cities. Jim Fisk of LaunchPoint Technologies in Goleta, California, is developing a Maglev system he calls the Magnet. The Magnet uses a stabilized permanent magnetic system, which allows trains to float above the guideways without wrapping around them. And because they aren't attached to the guideway, trains could reroute and switch on the fly.
You can't have a network system without good switches. The internet would not work at all without really good high-speed switches. If we're going to make a new network that is fundamentally better than mass transit systems of the past, we have to have dynamic instant switching. It's a critical part of it.
Switching is controlled by a computerized system that increases and decreases the magnetism as needed, so that the train can never derail. Magnetism is also used to power the train. A magnetic rail in the center of the track tugs on power coils mounted in the train, pulling it forward.
And a number of these electromagnets in the vehicle all attracted or repelled from permanent magnets in the track. And you electronically turn them on and off at the proper time so that you're always getting forward thrust.
Fisk envisions his magnet working like modern elevators, which tell you which car is going to your floor. His system will redefine our ideas about local versus express trains.
The old paradigm is you go to the station, you wait for the train to arrive, you get on the train, then you wait on the train while it stops at all the stations in between where you started and where you eventually want to go. The new paradigm is you go to the station, there are vehicles waiting, tell it where you want to go, and it takes you there.
So you won't have to tag along with hundreds of other passengers just for the ride.
The key is you have smaller cars, you have more cars, and you have them dynamically routed. Because of the switching, you can send cars to the places where they need to go rather than where they're scheduled to go.
The Magnet will become your personal train service.
We're talking about door-to-door service.
The promise of Maglev technology could redefine the transportation landscape.
The technology is the only one that I know of that's capable of providing the switching and cost effectiveness that will be necessary for transportation systems of the future.
But if it's raw speed you're looking for, Maglev will have competition. Lightning-fast steel wheels on rails are already here, and they're getting a complete overhaul that will make them even faster. Just because some future trains will be floating on magnets doesn't mean we've got to throw out the tracks we've already got. Forward-looking designers are pushing the speed limits of steel wheels on rails to come up with trains that will compete with Maglev. Think it can't be done? Take a look at what they've been doing in France. This is the TGV, the train à grande vitesse, or in English, simply the high-speed train. For more than 20 years, it's been the standard bearer for rapid rail travel. And for a lot of locals, it's replaced air travel between cities.
Ce que l'on veut, c'est offrir un train dont le temps de parcours soit compétitif par rapport au temps de parcours de l'avion. le choix entre l'avion, la voiture et le train, ils décident de prendre le train à grande vitesse.
To get even more passengers to jump on the train, the French rail company Alstom has been building newer versions of the TGV that go faster and faster. A test model was pushed up to a blistering 356 miles per hour. A world record for steel wheels on rails. At that rate, you could get from New York to LA in less than 8 hours. Chicago to New Orleans in 2.5.
Bon, c'est sûr qu'en battant le record du monde, Alstom s'est donné une marge de progression par rapport à ce que l'on peut faire en termes de vitesse dans le futur.
But the TGV's record-breaking run was only a test under special conditions. In regular operation, the TGV clocks a still impressive 200 miles per hour. For years, this was thought to be the outer limit for a passenger train. After all, how fast can a train really go? The friction of the rails and the huge bulk of the trains themselves would seem to impose some pretty severe speed limits. But now, the creators of the TGV are testing those limits with their latest prototype, the AGV, expected to go at least 10% faster than its predecessor.
Il y a quelques années, vous m'auriez dit rouler à 360, est-ce que ça aurait été possible? On aurait sûrement répondu non. Maintenant, on vient d'étudier des trains et de commencer à les fabriquer qui peuvent rouler à ces vitesses-là.
In order to hit those speeds, the AGV had to shed some weight. The first thing to go, the heavy locomotive. Instead, the designers put powerful motors under each passenger carriage. Then, they thinned out the train's bulk by using carbon composites in place of steel. Next, the wheels. The AGV's articulated design calls for 20% fewer wheels than a conventional train, making it lighter and more aerodynamic. And that articulated design means the train's cars are fused into a single tube, which makes the AGV a whole lot safer if there's ever an accident.
Il n'y a jamais eu de mort dans aucun accident avec nos trains à grande vitesse. Je pense que ceci est dû à...
But there's another problem designers are going to have to solve if we're going to race into the future on rails. That's the problem of curves. In recent years, engineers have been working on ways to navigate winding tracks by using tilting technology. A new class of trains is learning how to lean into the curves like a speed skater. Nowhere is this technology more critical than in mountainous parts of Japan. Winding curves have been the worst enemy of the country's famous bullet trains, forcing the fastest trains to slow down dramatically. But a new train that combines tilting technology with a smart sensor system is about to change all that.
カーブが来た時に適切に車体を傾けるという制御を行います。
This is the N700, a futuristic bullet train that's taking curves head-on by speeding right through them. The first car is outfitted with a sensor that detects curves and sends a signal along the 16-car length of the train. Each car then falls in line, leaning into the turn using an air spring system underneath each one. It all adds up to a train that can take curves at the same speed as the straightaways, while passengers roll along without even feeling the turn.
新幹線、鉄道特に新幹線は非常に高速であるばかりでなく快適なおかつエネルギー的
The N700 not only saves energy, it actually generates it. Regenerative braking technology captures energy every time the train slows down. That energy is sent back to a substation and used by other trains, turning the N700 into a rolling power plant. But as fast and efficient as the N700 is, the next generation of Japanese trains is expected to blow it away. The experimental FastTech 360 has a carriage designed to blast through any snow on the tracks. And since it's expected to routinely clock around 250 miles per hour, to slow down, the FastTech uses flaps like an airplane, earning it the nickname Cat Ears. All these new designs are forcing us to rethink our expectations of what trains can do. And it's not over yet.
Nous ne sommes pas aujourd'hui à la limite de la vitesse. Dans 20 ans, il est très vraisemblable qu'on ira encore un peu plus vite.
To elevate trains to a whole new level, tomorrow's trains will float, slide, and fly. And they won't need tracks, at least not the kinds of tracks we would recognize. What if we could build tracks out of nothing but air? That's the vision that inspired Yasaki Kohama, inventor of what he calls the Aerotrain.
Aerotrain is a kind of symbol for the future green society. The Aerotrain is partly train and partly aircraft.
Kohama's train is designed with wings and rides on a cushion of air thanks to an aerodynamic principle called wing-in-ground effect. Because of interference between the wing and the ground, a plane that is flying very low experiences more lift and less drag than one flying at higher altitudes. It's the same principle that causes a sheet of paper to flutter when dropped. Kohama discovered he could exploit that effect by creating a half-enclosed concrete track and flying a train along it with incredible energy efficiency. The wing-in-ground effect gives the Aerotrain just enough lift to keep it aloft, but not so much as to make it fly off the tracks. To move forward, all the train needs is a little push, which it gets from its solar-powered electric propellers.
The electricity needed for pushing the Aerotrain is very low, so that we could utilize the only natural energy resources for generation.
In fact, the Aerotrain will use only a quarter of the electricity required for maglev trains. At top speeds, the Aerotrain could hit 270 miles per hour, and each train could carry up to 350 passengers, making this flying train perhaps the most energy-efficient and cost-effective way to travel in the future. But Kohama isn't the only train innovator fascinated with air. Sheldon Weinbaum at the City College of New York thinks he can make trains ski over nothing but fluff. That's right, fluff. Who would come up with an idea like that?
That may seem like an insurmountable task. The point is, it isn't.
Weinbaum's idea didn't come from the world of transportation, but from snow. Intrigued by the way skiers move over snow, Weinbaum decided to head to the mountains. He ran some experiments with a skier and realized that as a ski glides over snow, the air trapped underneath keeps the skier lifted as she moves forward.
You frequently meet people who are expert skiers, and they will always tell you that when they ski on fresh powder, they feel like they are skiing on air. And indeed, that is what's happening.
But Weinbaum wanted to take it a step further. Could he turn a train into a giant ski? Could he design a track that would provide this airlift and therefore create a super fast and almost frictionless new form of travel?
One of the things that we had realized was that there was a tremendous potential for enhancement of lift. We could increase the lift by 1,000,000 times.
Weinbaum developed a theoretical framework that would be able to lift a 70-ton train with 200 passengers. But he had two challenges: building a track that would keep air from escaping and looking for material that could provide pockets of air, like snow. To figure out how it could work, Weinbaum went shopping.
We actually went to Bed Bath & Beyond, and we picked up a material that is used to fill inexpensive body pillows.
With his collaborator, Yannis Andriopoulos, and his students, they used the fluff to mimic snow. Their experiment showed that in principle, a train moving along a track filled with synthetic fluff could reach airplane speeds with minuscule amounts of energy. The next step is to build a working prototype, which Sheldon Weinbaum hopes to do soon.
The technology is relatively simple. What seemed like a dream, I think, is much closer to reality.
But while fluffy tracks may have a promising future, securing land and laying down any kind of tracks is still one of the most expensive and complicated parts of a rail system. So what if trains didn't need to be on land? And what if they didn't need any tracks at all?
The solution is not the train, it's solving the cost of the track. So our attitude was, well, what if you could take the railroad and the train apart and put it back together a little bit different?
Robert Pulliam's tubular rails are trains that run through a series of elevated O-rings instead of on a track. What Pulliam proposes is to take an old idea and turn it inside out, literally.
We've put the steel wheel inside the rings. We've put the rail on the car itself, so it essentially carries it along with it.
Each ring will have a motor that drives a set of steel rollers, and these rollers will fit into grooves built into the train itself, passing the train from one ring to the next. The train is secured in place by 3 rings at all times, and its body will be reinforced so that it can never slip or break.
Once the vehicle is in the rings, it really cannot escape. It's much like holding a pencil in your fist and holding it tight. There's only 2 ways that pencil can move. You need more horsepower during the acceleration phase, but when you're at a constant speed, it really doesn't take that much energy to keep the vehicle moving. It's really the momentum.
Pulliam's design dramatically cuts the highest construction costs, the rails themselves. And tubular rails can be stacked on top of each other, so it's not just a space saver. It can be built with no interruption to any existing infrastructure. That means no more collisions with cars on the road or even other tubular rails.
You operate in the airspace rather than on the ground space.
Pulliam sees his tubular rail system fitting within a city and also connecting major metropolises. At its top speed, it could hit 150 miles per hour.
The 2 markets we feel that have applications are a high-speed market, something that you would have a vehicle running at, say, 150 miles an hour. The other market is the commuter-type rail system.
And significantly, the technology for the tubular trains of tomorrow is here today.
The key thing is changing the orientation between the rail and the wheel. All of the components exist.
According to Pulliam, it's not just changing the orientation of the track, it's about changing the way we think about trains. We won't just be jumping through hoops, we'll be racing through them at lightning speeds. Floating, flying, or fluffy, the tracks of tomorrow are bound to be very different. But one of the most surprising things about future trains may be where they'll get their power. From sewage.
I believe we have a way to use bacteria to make renewable energy.
Compared to a stop at the gas station or the cost of jet fuel, most people riding trains don't think about how much fuel it takes to move along the rails. But trains have actually been one of the biggest gobblers of fossil fuels, whether in the form of coal, diesel, or rails electrified by polluting power plants. Nowhere is the problem of polluting trains bigger than in the rail freight industry, where companies like Burlington Northern Santa Fe haul millions of tons of goods every day over thousands of miles of tracks.
We burn over 4 million gallons of fuel a day. That represents about 2.2% of the entire consumption of fuel in the United States, as well as 30% of our total operating cost on the railroad.
Burlington Northern Santa Fe, one of America's largest rail freight companies, has 6,300 locomotives hauling 220,000 freight cars. On any given day, BNSF is the single largest consumer of petroleum-based fuels in the world, surpassed only by the U.S. Navy during wartime. But that's something they're looking to change.
At Burlington Northern Santa Fe, we are committed to our environmental stewardship. As one of the largest Class I railroads in the nation, we take it very seriously.
They take it so seriously that BNSF has now committed itself to building the locomotive of the future. A locomotive powered by a fuel which will never run out: hydrogen.
Hydrogen is inexhaustible as a fuel. Hydrogen is the most abundant element in the universe, by far. It's made up of only two fundamental particles, a proton and an electron.
Arnold Miller of Vehicle Projects is teaming up with BNSF to try to power a train with nothing more than hydrogen. Because hydrogen is so simple and so abundant, it's considered a universal fuel, which can be extracted from ordinary water. Their design calls for replacing the train's enormous engine with a much smaller and cleaner fuel cell.
A fuel cell is a power device analogous to an engine. The input is chemical energy of a fuel, and the output is electrical power.
A hydrogen fuel cell is a device which turns hydrogen into electricity. Hydrogen atoms stored in the cell interact with oxygen from the air. The result? Electrons are stripped from the hydrogen, creating electricity. The only byproduct is H2O, water. And at least in theory, a fuel cell is twice as efficient as an internal combustion engine.
In today's environment, the railroad can move a ton of product, 430 miles on a gallon of diesel fuel. If you translate that into what we can do with hydrogen, it would make a tremendous impact on our ability to ship product.
Eco-scientists are still trying to work out ways to efficiently manufacture and store large amounts of hydrogen for fuel cells. But at Burlington Northern Santa Fe, they're betting on a vision of freight trains that are clean and green.
What's so exciting about this project is that even though this project is in its infancy, one can only imagine the potential and the possibilities of this type of technology.
Trains will revolutionize our global transportation infrastructure because they'll be fast, safe, convenient, and sustainable. And sustainable trains will be trains powered by hydrogen. But so far, our future trains are facing a slowdown because getting hydrogen from water is proving to be difficult and expensive. Bruce Logan is a garbage man, and he may have a better way.
There's a lot of energy in organic matter, and that's why bacteria eat it and break it down. But when we make hydrogen in the process, we can capture about 80 to 90% of that energy as hydrogen gas.
Okay, Bruce Logan isn't really a garbage man. He's an environmental engineer, and he sees future trains powered by hydrogen that comes from waste.
When we say waste, we mean anything that's biodegradable that's not being used for another purpose. So, for example, wastewater from humans. It could be animal wastewaters. It could be a food processing wastewater. It could be food that was not eaten by people. Virtually anything that's biodegradable.
And believe it or not, this slop could be what runs future trains.
We realized that to develop any sort of sustainable transportation infrastructure, we're going to have to capture energy from waste sources and using that for useful purposes.
To turn waste into fuel for trains, Professor Logan has developed a very unusual power station, a microbial electrolysis cell. Inside the cell, bacteria live and breathe, and in the process, produce hydrogen.
The key is to not let bacteria have oxygen. We put them in a device which keeps them separated from that oxygen, so these electrons flow along a circuit making current or electricity.
In the absence of oxygen, bacteria living in Logan's device release protons and electrons. When a small jolt of electricity is added, these particles fuse into a usable hydrogen gas. The combination of waste and bacteria to produce hydrogen could re-energize the railroads. Today, trains rely on oil wells and coal mines for fuel. Someday, they'll rely on farms and sewage plants for hydrogen.
What are trains going to do when they cross the large distances of the Midwest? They're going to need to refuel. And why not refuel on material that could be generated across the country, where we could envision these towns along railroads taking the energy from crop wastes and turning it into hydrogen right there and using that hydrogen to refuel trains. Right now, we can't imagine that happening, but 100 years from now, it could be very likely.
Scooping up garbage for fuel as they go, the trains of tomorrow will hurtle across the country quietly and cleanly. Will we see the end of the highway? Will traffic jams, gas guzzlers, and car accidents be a thing of the past? What if we turned the highway into a train? Those are questions Frank Randack asked himself.
The basic idea of driving yourself at high speeds in a car is just outdated. It's inefficient and it's dangerous. So we have to find a better way to solve the highway problem. And it should be automatic, and it should be safe, and it should be high speed. The AVT does that.
The AVT, or Advanced Vehicle Transport, is Randack's vision for a future of constantly moving trains shuttling us along, just like highways, but on automatic. That's Frank Randack's dream, and it was born, not surprisingly, in the middle of a freeway traffic jam.
I was on the Golden State Freeway in Los Angeles, going about 5 miles an hour, and I said, there's got to be a better way. This is absolute insanity.
Anyone who drives a car knows that frustration all too well. But how many of us would actually turn irritation into innovation? Randack knows his idea seems outlandish, but he has a singular vision.
It's very difficult to get new transportation concepts accepted, and that's the battle. But the AVT is an idea whose time has come.
The AVT will resemble a vast conveyor belt, never starting or stopping, just constantly moving at the same high speed. All you have to do is hop on. Drive to a departure station and pull onto one of the automated shuttles. The shuttle will get your car up to speed and automatically load you onto the train. The AVT uses maglev technology and runs continuously on elevated tracks parallel to the highways.
One AVT track on the one side of the freeway is equivalent to 5 lanes. It'll transport 10,000 cars per hour.
And it will be a lot more comfortable than driving yourself.
There's public transportation, which is private and nonstop. You have the same amenities that the cars do. You have restrooms, you have entertainment in the front, and refreshments. Essentially, every place where there's traffic, there should be a train. I don't see any reason why all highways should not be automated.
And the AVT will be remarkably clean, using solar power during the day and battery power at night.
It's a wonderful solution, and the entire train can be powered pure solar, requires no energy, no fossil fuels.
And virtually no effort on the part of the driver.
Being able to go a 100, 200-mile trip in minutes rather than hours. It would change everybody's life.
But what if our future automated highways didn't just use clean power, but actually generated it? Could one of our worst energy problems become our greatest solution?
In the future, I see an integration of public infrastructure systems using high-speed, elevated maglev rail systems like the hydrogen superhighway, or the HiRail as we like to call it, It'll change the way people move, change the way people get to work, and distribute hydrogen to all the gas stations along the highway.
Justin Sutton wants to create what he calls the Interstate Traveler, an all-in-one solution to a city's infrastructure problems that would combine transportation and power supply. So not only will this train shuttle you from place to place, the track you're riding on will supply energy to the city you live in.
The system self-sustains because of the solar panels that are mounted on top of the rail. We support an average of 85,000 square feet of solar panels per mile of rail, which will generate about a megawatt per mile per hour. That gives us all the power we need to run all of our subsystems and to keep the transportation moving 24 hours a day, 7 days a week. It'll generate an enormous amount of power. Building 2,000 miles of this rail in every state is like having your own Hoover Dam right in your own backyard.
But the Interstate Traveler isn't just a source of power. It's a versatile rail system that could support a wide mix of vehicles, private and public, carrying pedestrians, automobiles, and freight. The system can support massive vehicles weighing more than 6 tons each, pulled along the rails using maglev technology.
Today, our highway systems can only hold about 2,000, maybe 3,000 cars per mile in bumper-to-bumper traffic. When you have a city of over 1 million people and you need to evacuate that city from a natural disaster, it will take 400 miles of highway just to absorb 1 million people. And we'll be able to move 1 million people a day without any problem whatsoever.
Even today, fully automated transit systems are starting to appear in some of the world's great cities. Beneath the streets of Paris, the new Meteor train is shuttling passengers like clockwork, no delays, and no driver.
Métro, maintenant, la même évolution qu'on a vue dans les ascenseurs. On a maintenant le métro qui se déplace automatiquement.
The Meteor is Paris's first fully automated train, cutting across a 5-mile east-west stretch. Controlled by a central command center, this system can pinpoint any train's position, regulate speed, and ensure no 2 trains collide. Going automatic means that train traffic can be increased, while your wait time between trains decreases. No station will ever reach critical mass. You wait only 90 seconds until the next train sweeps through the station. And in the distant future, could we build a train that would get us anywhere on Earth in 42 minutes and 12 seconds?
As you get toward the center of the Earth, you accelerate to up to 18,000 miles per hour.
Hydrogen and solar energy may fuel our future trains. But what if it turned out that the most powerful alternative fuel of all might be the one right beneath our feet?
The gravity train is fantastic. It's stupendous. It could solve all our transportation problems.
That's right, the gravity train. It's an idea that's been around for centuries. And if it can be achieved, someday you'll be able to travel to any place on Earth in just 42 minutes.
Imagine going from Tokyo to Paris, Prague to LA, Reykjavik to Seoul, all in 42 minutes.
No supersonic engines, no turbojets. All you need, gravity. It sounds crazy, but in theory anyway, it could happen.
Hey, on paper, it seems to work. Believe it or not, if you want to go to China and you could somehow drill a hole through the center of the Earth, it would only take 42 minutes and 12 seconds for a one-way trip to China. This is sure faster than a slow boat to China.
Assuming you could drill a hole like that and suck the air out of it so there was no resistance, the force of gravity would essentially let you free fall all the way down to the center of the Earth.
If you get into this gravity train and you hit the down button, basically you're in free fall. As you get toward the center of the Earth, you accelerate to up to 18,000 miles per hour.
And then, once you pass through the Earth's core, you'd start to gradually slow down, with gravity acting as a natural braking system as you glide to your destination.
The path is symmetric. As you accelerate, going to the center of the Earth, then you decelerate on the other side of the Earth.
Total travel time, 42 minutes and 12 seconds. Sounds pretty good, right? So why aren't we building one?
There are two basic hurdles to building the gravity train. First is you have to build a frictionless tube, and you have to evacuate all the air. You don't want to ride on a cushion of air, because then you can only go about 120 miles per hour, and you want to go up to 18,000 miles per hour. But the second problem is perhaps the greatest, and that is as you drill toward the center of the Earth, it gets enormously hot. In fact, at the center of the Earth, it's about 10,000 degrees Fahrenheit. So you would have to have enormous construction materials to keep the elevator tube from melting, from being crushed by the enormous pressures down there. This is an engineering problem that we have simply not been able to solve.
So you might not be crossing the planet by gravity train anytime soon. But it turns out you wouldn't have to go through the center of the world to enjoy the benefits of gravity.
Perhaps in the future, if we drill at an angle, at a very shallow angle, rather than to the core of the Earth, then perhaps we won't encounter such enormous pressures and temperatures, and then we might be able to evacuate this tube to create a frictionless gravity elevator, a gravity train, that'll take you anywhere on one side of the Earth in 42 minutes.
A shallower angle would mean you'd get less direct tug from gravity. But then again, your total travel distance would be less. The physics are such that no matter what angle you took, your travel time would be exactly the same.
The longer the track, the faster you move, and the two effects just balance each other out exactly. And that's why it only takes 42 minutes, 12 seconds to go anywhere on the surface of the Earth. This could revolutionize travel on the Earth.
So, someday, if we can work out the small details of crushing pressure and vaporizing heat, you could spend your lunch hour shooting from New York to Miami or New York to Beijing. But the revolution in train travel isn't waiting. It's already begun. Soon you'll be racing on rails at hundreds of miles per hour, using the power of magnets to glide between and across cities, floating and skiing on brand new kinds of tracks, in trains powered by hydrogen and the sun, cruising along automatic highways, and just maybe catching an express right through the planet. These are future trains.